Okay, so in this class, we'll discuss from question 14 till how much we can cover, let us see. Okay, so go to your tuition note, page 112. Okay, we'll start with that thing called momentum today, question number 14. Okay, what is momentum? Let us read through that once. We can just figure it out, I think. The effort, look at your note there, page 112, tuition note, okay. Effort is needed to stop a moving object like a ball, for example, right? If a heavy cricket ball and a light tennis ball are moving together, so you roll a tennis ball, a light one, and a heavy cricket ball like this size, roll it with the same velocity, okay, together with same velocity, then lesser effort will be needed to stop the light tennis ball than the heavy cricket ball. So even though the two balls are rolling with the same speed, when you put your hand to stop it, you'll feel that you need more force to stop the cricket ball because it's heavier. Okay, so keep that in mind. So this effort that you put to stop the two balls needed to stop the moving object is a measure. This is indirectly measuring the amount of motion in the ball. So even though the two balls are moving same velocity, the amount of motion in the two balls are not same. The amount of motion is more in the cricket ball because you needed more force to stop it. So that amount of motion contained in a moving object is called momentum. Okay, so you tick there. Yes, second paragraph. In simple terms, this amount of motion present in moving object is called momentum. So in simple language, simple understanding, the amount of motion that is there in any moving object is called its momentum. Okay, so here, if you roll a tennis ball and a cricket ball with the same speed, you can see they're moving together with the same speed. You need more force to stop the cricket ball because it's heavier. So we say the amount of, even though they're moving with same velocity or speed, the amount of force you need to stop the ball is higher for the cricket ball. So we say the amount of motion in the cricket ball is higher, even though it's moving with the same velocity. I hope you're getting it right. So here, another example you can take a round size of a chalk, okay, the one we write on the board, and another iron ball of the same size. Both are same size, but iron ball is heavier. If you throw it onto this board with the same speed, we know the iron ball will produce more sound, means it has more momentum, even though they are moving with the same speed to the board. So we say the iron ball has more momentum. So a momentum is the amount of motion in a moving object. Okay, so the technical definition is 15. Let us read through that. What is momentum? Give its SI unit. Okay, so the momentum denoted by P of an object is defined as the product of mass and velocity. So technical definition is 15. Question number 15. Momentum is denoted by P, and it is the product of the mass of the object multiplied to its velocity. So that's the definition for momentum. So the SI unit we can understand. So SI unit, you write down. Unit will therefore be, you write this formula, momentum, M into V. Write along with me. As you write like that, we know the SI unit for mass is, SI unit follows the MK as basic unit. So mass is kg. To measure distance is meter. To measure this mass is kilogram, kg. To make this one is time in second. So SI unit of mass there you can see is kg. And in the previous chapter, velocity is displacement. SI unit of displacement is meter. Time is second. The displacement by time. So in our previous chapter, we learned SI unit of velocity is meter per second. So when we combine all this, we're going to get kg meter per second. This is the SI unit of momentum, kg meter per second. So understand how it is coming out after this. After that, memorize it. Okay, I'll go to the next question. Question 16. Write some important characteristics of momentum. So as we said, momentum is simple terms, amount of motion in a moving object Technical definition is mass multiplied to velocity of a moving object. Mass of the object multiplied by its velocity. SI unit is kg meter per second. Now let us see some characteristics of momentum there. A. Momentum has direction. Not only the magnitude, but it has magnitude and direction. So any physical quantity that has magnitude and direction is called scalar vector quantity, right? So there on your note, correct that scalar. It should not be scalar, rather vector. A quantity defined by only magnitude, like height of a boy, is scalar. But momentum, we have to define only magnitude is not complete. We have to mention the direction also. Direction of momentum is very important. Therefore, it's a vector quantity. Now, number B, its direction. So the direction of momentum will be the same as the direction of the velocity. In what direction the velocity of the moving ball is moving is also the direction in which the momentum will be imparted. Okay. SI unit of momentum is kg meter per second. We know how it is coming out. See D there, page number 113, tuition note. Since application of unbalanced forces bring change in velocity of object, therefore it is clear that a force also produces change in momentum. So if this ball is rolling with a certain velocity and you go and push it, make it higher, the momentum will increase. So if it's moving and you want to stop it, you have to apply a force of your hand. So the momentum will decrease. So to change momentum to increase or to decrease, we need some outside force. Okay, so that's what it means. Now, number 17. This we can just read and understand, I think. Change of momentum is not only determined by the magnitude of force, but also by the time duration of the force exerted. Proof with an example. Let us read. Let's say a car with a dead battery. So the car is not starting by itself, igniting by itself because of the battery on a straight road. To give it a speed of 1 meter, so we want to push it with hand to give it a speed of 1 meter per second, which is enough to start its engine. So as you push, the engine will start. If one person, or if one or two persons alone only give a sudden push, that is a force to it, the car will hardly move. But a continuous push, so if two persons come and just push with high force also, just for sudden, the car will only a little bit move and stop. But if the two persons continue to push like this, push like this, push like this, the car will begin to move. That's what it is saying. Okay, so here, but as the continuous push over a longer period of time results in gradual acceleration of the car to this speed. So the car begins to move to this 1 kilometer per hour, 1 meter per second, sorry. This means that change in momentum of the car is not only determined by the amount of force, high force that two boys put also. Only sudden, it doesn't move the car, but same force continuously applied for longer time increases the momentum. So momentum is not only about how much force you put, but also how much time you apply that same force also increases or decreases the momentum. So momentum is determined by two things, magnitude as well as amount of force. The more force you put, the more momentum you get. But not only that, the amount of time you apply that force also increases or decreases the momentum. So thus this example proves that, right? Thus it can be concluded that the force necessary to change momentum of an object depends on the time rate at which momentum is changed. So not only the force, but the amount of time that you put the force, right? Question 17. So let me read the next one, the next part. Question 17 above can also be this way. Question can come this way. The force necessary to change the momentum of an object depends on the time rate at which momentum is changed. Proof with an example. Same. The more time you put on the car to push, the momentum increases, right? So this proves that not only the amount of force, but the duration of the force applied is duration of force means force divided by time. So time, that's why it's called rate, time rate. Now let us go to the next one, number 18. Newton's second law. First law we have discussed, which says that the tendency a body at rest will continue in rest, and a body in motion will continue in its motion of uniform motion until and unless an outside unbalanced force interferes. Second law, let us see. Newton's second law, page number 114. of motion states that the rate of change of momentum of an object is directly proportional to the applied unbalanced force and takes place in the direction of the force. So directly proportional, question number 18, write down. Let me give you an example quickly. Directly proportional, then we will explain it. So directly proportional, a simple example you can take here. Price of one sweet, let us say a particular kind of sweet, multiplied to number of sweets that you're buying, let us say, okay, will be equal to total price. You know that. Now let us say the price of sweet that you buy, that particular sweet, is rupees 10. You buy one sweet, then the total price will be rupees 10. You're getting, right? Then you increase this one, rupees 10, price of one sweet will not change. If you buy two, it will become rupees 20. This rupees 10 price of one sweet will not change. If you buy four, comes rupees 40. 10 fours are 40. So you see here, which is not changing. Yes, that's right. This price of one sweet is not changing. So that is called a constant, okay? Constant in an equation. Then what are the two changing? Number of sweet change, price, total price change. How? Number of sweet increase from 1 to 2, total price also increase from 10 to 20. Number of sweet increase to 4, total price also increase to 40. So we see that as we increase the number of sweets on the left side of the equation, total price is increasing. As you decrease it, the total price is decreasing. This relationship between number of sweets and total price is called directly proportional. That means an increase on one side, number of sweets, causes an increase on the other side, total price. This kind of relationship is called directly proportional. So let us read once more. Question number 18. Newton's second law of motion states that the rate of change of momentum of an object or body is directly proportional to applied unbalanced force. Means the rate of change of momentum will, if it increase, okay, then the force is increased. If you increase the force, the rate of change of momentum, the momentum is also increasing. Increase in force, increase in momentum. That's called directly proportional. So let's go to 19 and we'll understand better again. We'll derive the equation for second law of motion. Question number 19. Let me read the question. There it says, derive the mathematical equation for the second law of motion. Let us say an object of mass here. Okay, so let's just write down the answer. Let's say an object of mass m is moving along a straight line, in straight path, with initial velocity, let us say u, initial velocity u. It is uniformly, okay, accelerated to velocity, that means final velocity v, in a time period of t, let us say, by the application of a constant force, means a fixed force, not constant means not changing, F, okay, throughout, so throughout the whole time, throughout t means throughout the time, the initial momentum, let us denote by P1, and final momentum, let us denote by P2, will be, let us say, we know just now by the definition of momentum is mass m. As you can see, into initial momentum means initial velocity u, equation 1, let's say, and final will be mass of the same object multiplied to final velocity. Final momentum means multiplied to final velocity. Let's say this is equation 2. Now here, so change in momentum. So change in momentum according to second law is directly proportional to change in momentum. So change in momentum means final minus initial, so P2 minus P1. So this will calculate the force, change in momentum, directly proportional to P2 minus P1, right? Then which is equal to here, P2 is mv minus P1 is mu. As you can see, equation 1 and 2. It's using equation 1 and 2, equation 1 and 2. Now next here, as we continue doing it, that will be here directly proportional to m is common, you can take it out, v minus u. We can write like that. So once we're through with that, now here, then let us say change in momentum is here. Let us say here now rate of change of momentum. So if we put the word rate of change, okay, so the pen seems to be having problem. Anyway, let's see rate of change of momentum. Rate of change, the word rate of change means rate of change. When the word rate comes, means anywhere you see rate means divided by time. So here m into v minus u, m into v minus u, v minus u divided by t. That's the meaning of momentum. Okay, t. So once we're through with that, then let us write down here rate of change of momentum. Now we will remember here now. Here, rate of change of momentum. So now rate of change of momentum is nothing but F. The definition of rate of change means momentum divided by time is called force. So replaced by that, force in directly proportional to. Now this is m, so we just write it and write here, since we know here v is equal to u plus at. So we know that a will be equal to v minus u, will go this side, means minus u divided by t. We know this from our first chapter of motion. A is v minus u by t. So here v minus u by t is a, so we can replace by acceleration. Then here, if you remove proportionality sign and put equal sign, constant must come in, k into ma, where this is called a constant of proportionality. Now for convenience sake, we always put this one so that k, when k equal to 1 unit, okay? So when you put it as 1 unit, you're going to get the equation for second law of motion, which is therefore F will be equal to 1 into ma. That is, F is equal to ma, the famous equation, second law of equation. Force is equal to mass into acceleration. So keep this one in mind. We're going to do numericals most probably in the next class. Next year, let us do, go to the next page, page 115. So there, question number 20, okay, 20. Now, the SI unit of force, question number 20. Maybe we can conclude there for today, and then we can continue in the next class. SI unit of force. So let's do that. Question number 20. SI unit of force. Fill in the blanks. Now below this you do. Just now we got F equal to ma. So let us do SI unit of mass we know is kg. In the previous chapter we know SI unit of acceleration is meter per second square. Acceleration is velocity divided by time, and velocity is meter per second. Time is second. So if we shift this up, meter per second into this go up means second to the power plus 1 also will become minus 1. So meter minus 1 minus 1 minus 2. So meter per second square. That's how you're getting it. So the SI unit of forces today we learn kg meter per second square. So kg meter per second square. SI unit of momentum is kg meter per second. Momentum is kg meter per second. Force is kg meter per second square. And this is written in short as simply in honor of the scientist Newton. You can write N capital Newton. But the best actual unit is kg meter per second square. Okay. Yes, tick there yes after you understood it. So this concludes the class for today. We'll continue in the next class. Okay.